Today I'm going to be talking about two types of renewable energy and how they can address climate change, solar energy and biomass. And I want to start, though, with just a few words about the urgency of the climate change problem. This graph shows the various scenarios that were established by the Intergovernmental Panel on Climate Change back in the year 2000. And those are the different colored lines that appeared there. And if you look at these lines, the very worst case is this red line. That's A1FI, the FI stands for fossil intensive. That's their worst case scenario. If you look at these white circles, and then finally the red dot in 2006, that indicates the actual world carbon emissions. So the point I'm trying to make in this graph, thanks to Chris Field of Stanford University, is the fact that world carbon emissions have exceeded the worst case scenario developed by the IPCC. So you can see this is, I'm going to give sort of a good news, bad news story this morning. And I'm starting with the bad news, but don't worry, I will get to some good news. You're probably familiar with the fact that the IPCC came out with its fourth series of reports since 1990, back in 2007. And after that report came out, a number of scientists were concerned that it might be too conservative. As you probably know, certainly it's an excellent set of documents. But scientists look at the research over the previous 6 years, and in fact, things are evolving very rapidly. The other thing is that these reports have to reach consensus, and government representatives are involved in that consensus. So again, they tend to be somewhat conservative. So here's an article that appeared in Science in June 8th of 2007. And here's what it said at the beginning of the article. The scary side of global warming, greenhouse warming might be more disastrous than the recent international assessment managed to convey, scientists are realizing. But how can they get the word out without seeming alarmist? So let's talk about what the latest IPCC study does not include. And if you read the physical sciences report, it's about a 1,000-page report. Most people, including myself, just make it through the technical summary and the summary for policymakers. But if you look at that report, they will say many, many times throughout the report that they were unable to model future rapid dynamical changes in ice flow. So for example, their sea level rise projections include thermal expansion of the oceans that's associated with the warming. It also includes melting of mountain glaciers. What they haven't been able to account for is what's rapidly happening right now to the land-based ice sheets. This is a fairly famous photograph, but there have been more like this. And this shows you a meltwater stream in Greenland. And one of the things that the scientists try to emphasize is that when ice builds up, it's a slow, gradual accumulation of snow, and that gets compacted. And we see that, for example, in the center of East Antarctica, where there's snow accumulation there. It's a very gradual process. But once the ice starts to melt, there are many positive feedback mechanisms which cause it to accelerate. And so once the water starts to flow here, for example, you get all this heat and mass transfer associated with that water flowing. Everyone knows how erosive flowing water can be. And in particular, what happens here is the water can dig its way down through what are called moulins. And these moulins can actually go all the way to the base of the ice sheet and lubricate the ice sheet, and we're seeing that in Greenland. So I have a couple slides on land-based ice, but I wanted to show at least one slide on the floating ice. This is the sea ice. And this is a slide that I've actually been showing for the past year and a half or so. And it shows you sea ice extent in the Arctic. And if you look at that blue band there, that is the range of model projections for sea ice extent. And that dotted black line, that's the mean of the models. Now, the red line is actually what we've been observing for sea ice extent. So the point is the sea ice is melting a lot faster than the models have predicted. That's because the models just are not doing a very good job of accounting for all these positive feedback mechanisms. Okay, so that's the slide I've been showing for about a year and a half. Now, the summer sea ice reaches a minimum every September. All right, so it expands in the winter, it contracts in the summer, and it typically reaches its minimum sometime in September. And the National Snow and Ice Data Center in Boulder keeps track of this. They use satellite measurements to measure the sea ice extent. And into September 16th of 2007, they recorded a new minimum. And so I'm going to plot now for you. That's the value in September 16th, 2007. So this is a value, the previous record low was set in 2005. This is a 22% drop from the previous low. So scientists perhaps 5 years ago were predicting we could be free of summer sea ice in the Arctic by 2100. And then there were researchers at NCAR that came out with a model a couple years ago that showed that we could be free of sea ice by as soon as 2040. Scientists now looking at this latest data say we could conceivably be free of summer sea ice by 2012, 2013. So that's within our lifetimes. Now, as far as scientists know, it's hard to know what the history of sea ice is because it doesn't leave a lot in the fossil record. But most of the scientists will tell you that we probably have not seen an Arctic that's free of summer sea ice in 130,000 years. So that's basically as long as our species, Homo sapiens, has walked this planet. And within our lifetimes, it looks like we're going to see the Arctic free of summer sea ice. Now, melting sea ice does not contribute to sea level rise. It's like the ice melting in a drink. When the ice cubes melt, it doesn't cause your glass to overflow because the ice is already floating and it's already displacing that fluid. But once that sea ice is gone, that sea ice tends to insulate the Arctic from warmer ocean waters. And it tends to affect the ocean currents. So once that's gone, we can see all sorts of effects take place. Now, what's going to happen next year? Well, maybe next year the minimum sea ice is not going to be quite that low. Maybe it's going to go back up again. But once that ice melts and refreezes, it's not as strong as it was before. So we're on this spiraling path of losing that sea ice. So I just want to show you a couple slides about the land-based ice. This is what really contributes to sea level rise. So this shows you Greenland, and Greenland has major outflow glaciers. And this is a glacier that's in a fjord. And if you look at this, what you're seeing in that fjord now is floating sea ice. It's where the glacier used to go. And those years show you what the extent of the glacier was. So this is the tongue of the glacier, and it's been melting over the years. It's been retreating. But notice the speed. This shows you how far it's moved in 50 years, 60 years. This is how far it's retreated in the last 5 years. So it isn't just that these glaciers are retreating. It's that their retreats are accelerating. Now what happens is, this ice in the glacial tongue buttresses the main glacier flow. And once this is gone, this main glacier can flow to the ocean much faster. So they measure the speed of the main glacier flow toward the ocean. That's it. That glacier is now moving toward the ocean at 5 feet per hour. Now I would ask you, when you think of something moving at a glacial pace, do you think of something moving at 5 feet per hour? It's really incredible. Okay, on the other side we have Antarctica. Now Antarctica, it doesn't have all the South Pole doesn't have, or the Southern Hemisphere I should say, doesn't have all the land mass of the Northern Hemisphere. It has a lot of ocean, and that tends to mitigate changes in temperature. So in the Antarctic, we're seeing warming on the West Antarctic Peninsula, but not so much on the main continent. And we are seeing ice slowly build up in the center of East Antarctica. What we're seeing is melt all along the coast, and melt especially in West Antarctica. And this shows you West Antarctica. You may have heard of the Larsen B ice shelf breaking off back in March of 2002. This is a floating ice shelf that extended out from Antarctica. And it was about the size of Rhode Island. And it broke away over a couple-month period back in 2002. So again, because it was floating, it did not directly contribute to sea level rise. But the point is, once that Larsen B ice shelf broke off, just like the tongue of that glacier that I showed you in Greenland, it was backing up that land-based ice. So what we see in Antarctica is after the Larsen B ice shelf disintegrated, we're seeing this one glacier moving 510% faster over a 2-year period, and another one moving up to 400% faster. All right, so this is land-based ice that's moving toward the sea, contributing to sea level rise. There was a recent article in Nature Geoscience just last month by Eric Rigno and his colleagues at Jet Propulsion Lab in Pasadena. They also do various satellite measurements. They've concluded that Antarctica, like Greenland, has a net loss of ice mass. Greenland set a record last year, by the way, for the amount of ice loss. And they've studied Antarctica over the last 10 years, and they find that the ice loss around the coast in West Antarctica is more than the snow accumulation in the center of the continent. So there's a net ice loss from Antarctica, and they've concluded that it has accelerated 75% in the last 10 years. So again, it's not just that the ice is melting, it's that the rate of melt appears to be accelerating. So what does this mean? Well, Jim Hansen, who's director of the Goddard Institute for Space Studies, says the last time a large ice sheet melted, and he's talking now 14,000 years ago, but there are other times in history, sea level went up 1 meter every 20 years. All right, so that's a little over 3 feet every 20 years. He honestly believes that if we keep doing what we're doing, we're going to have several meters of sea level rise by 2100. Now that's quite a bit higher than the latest IPCC report projects, but again, the IPCC folks admitted they were not yet able to model this rapid ice sheet disintegration. So he doesn't say this based on models, he says it based on previous history. We're rapidly approaching a temperature where this sort of sea level rise rate takes place. So is this going to start in 20 years? Is it going to start in 30 years? We don't know. But he personally believes a sea level rise of several meters by 2100 is quite possible. Well, what can we do about this? Well, according to Hansen, to limit sea level rise to 1 meter, and also associated with all this warming, is extinction of species. So if we want to limit sea level rise to 1 meter and we want to limit species loss to 20%, 1 out of every 5 species will be extinct by 2100. If that's our goal, and that seems to be an ambitious goal at this point, we need to limit additional warming to 1 degree Celsius, that's 1.8 degrees Fahrenheit, relative to the year 2000. Now this is a real challenge. One of the reasons it's a real challenge is, right now the Earth is not in balance. We have, since pre-industrial times, put enough greenhouse gases into the atmosphere that the Earth is no longer in radiation balance. What that means is there's more sunlight coming in than there is infrared radiation going out. For the Earth to come in balance, the Earth has to get more infrared radiation out past those greenhouse gases into space. How does that happen? The Earth has to heat up. When it heats up, it emits more radiation. So if we stop emitting all greenhouse gases today, some law, an international law was passed, we can no longer burn coal, we can no longer burn gasoline, we stop emitting all carbon today, the Earth is going to rise in temperature about another 0.5 degree Celsius, or roughly 1 degree Fahrenheit. That's if we stop everything today. That's already in the pipeline. That temperature rise is already in the pipeline. There's really not much we can do about that. And so limiting the additional rise to 1 degree Celsius beyond 2000, this is really a big challenge. People have been saying, and I'm going to talk to you about a report that we did for the American Solar Energy Society, a study that was done. But we used as a goal that we needed to reduce US carbon emissions somewhere from 60 to 80% by 2050. And I have to say, based on what we're seeing in the Arctic and the Antarctic, this number's been going up. A lot of people are now saying 90% reduction by mid-century. To get in that range, we need to limit our carbon emissions in the US by about 1,200 million tons of carbon per year, or if you will, 1.2 billion tons of carbon per year. So keep that 1,200 number in mind, because I'm going to show you the results of a study that looked at energy efficiency in various types of renewables and how much they can contribute to displacing carbon. And we're going to look at how it compares to that 1,200 number. So back in July of 2006, we had a conference in Denver. It was the annual meeting of the American Solar Energy Society. And we brought in some of the world's top climate experts. And this center photo on the top on the right is Jim Hansen. To the right, there in the corner, is Warren Washington from NCAR. These are some of the top climate scientists in the world. And they gave us presentations on the state of climate science. And I'll show you a website later, but if you go to www.ases.org, you can find a way to get the actual DVDs on the plenary presentations, and some of them, all of them really were quite excellent. But there's something else we did at this conference. We asked experts in efficiency and various fields of renewable energy to estimate, in more or less a crash program, what could your technology do to limit carbon emissions? And we chose not 2050, but 2030, because we thought if we focus on 2050, there's too many uncertainties. It's too far away for people to get serious about. Let's focus on something closer. And that's where that 1,200 comes from. That's actually the amount of carbon we'd have to reduce by 2030 to be on path for those 60 to 80% emissions reductions by mid-century. So what I'm going to do is I'm going to summarize a few results from this report. And I've been asked today not to cover all the different renewables, but just to focus on solar and biomass. So I will do that. I will give more details on those too. But at the end, I'll finish up just with a summary of the different contributions so you can see how they fit into the total. So here's a study, Tackling Climate Change in the U.S. And I have a copy with me, and I probably should have passed it around at the beginning of this, but I guess I'll pass that report around later. But it's a 200-page report. You can download a free PDF at www.aces.org/climate change. And it was released just about a year ago. So let's look at solar and biomass biofuels. Concentrating solar power is something that really holds a lot of promise. And I would have been here at this meeting yesterday. I noticed what excellent presentations you had lined up, and I really hated to miss it. But in Las Vegas, there was a 4-day meeting from Tuesday through Friday of about 450 people from around the world working in this technology, concentrating solar power. And I was involved in the sessions involving parabolic trough collectors, which are the collectors you see here. And these are the most commonly used collectors for concentrating solar power. But you probably have heard a lot about photovoltaics that produce electricity directly from the sun. In this technology, you use the heat of the sun just like you would use the heat from coal or natural gas, basically to boil water to produce steam to generate electricity. And because PV, photovoltaics, gets so much notice in the press, when I've seen one of the industry representatives talk about CSP, he often refers to this as the other white meat, taking off on the old pork ad. So what you're seeing here is a picture of a parabolic trough plant that was installed by Arizona Public Service outside of Tucson. It's a very small one. It's 1 megawatt. It's significant, though, because it was the first new plant in the U.S. in 15 years. Well, here are the different concentrating solar power technologies, and we divide them into two categories: dispatchable generation and non-dispatchable. What dispatchable means is it can provide electricity when the utility needs it, not just when the sun shines. How do you do that? Well, of course, the sun isn't always shining when the utility needs electric power, so you need some reasonably inexpensive storage, and when you can have that, you've got dispatchable generation. So those first two, parabolic troughs and power towers, are two different means of providing steam to generate electricity, but they use thermal energy, and so that can be stored in a tank. You can store a hot fluid. So here are the troughs, and this is a field in the Mojave Desert. They've been generating 350 megawatts for about the last 15 years, very reliably. This is a power tower. There have been 2 test projects. In this particular case, see in the trough case, what you do is you have typically an oil goes through the tubes in these receivers. And the parabolic trough reflectors track the sun, and they concentrate about 80-to-1 sunlight onto these receiver tubes. That hot oil transfers the heat to water. It's boiled. It produces steam to generate electricity. In the power tower approach, instead of moving a fluid through a field of collectors, you use these so-called heliostats or reflectors to reflect the sun onto a central power, and there you produce your steam, either directly or through an intermediary fluid. Okay, so those are the dispatchable technologies because you can store hot fluid and still boil water and generate steam when the sun's not shining. The lower two, we call it non-dispatchable. This particular one is a dish engine. You actually have a Stirling engine here that generates electricity. It's heated by the sun. It generates electricity. but it doesn't involve using any hot liquid. There's no easy way to do storage with it. This is concentrating PV. Sometimes it's done with a dish, sometimes it's done with flat like this and with individual little concentrators. But PV, again, produces electricity directly, and so you can't store it. I want to show you the importance of storage. This is the load profile. If you look at that blue line, that's the load profile for Arizona Public Service, which provides Phoenix with their electricity. And what you can see, if you look here, you'll see here's the load profile. This is a typical summer day, so air conditioning loads drive this, and it peaks in the afternoon or early evening, maybe about 5 o'clock or so. And then this is when the sun shines, this yellow. So clearly, there's some pretty good overlap, but not perfect. If we were just providing electricity directly with the sun, we'd be missing these early evening hours when people get home and they want air conditioning. If you use storage, we get the dotted red line. So we can, in the early part of the day, when we have more sunlight than the load needs, we can put that into storage and then use it later in the day. That's what we mean by dispatchable. These are the solar electric generating stations in the Mojave Desert. It shows you how much electricity they've been generating. On the left is their capacity in megawatts. They've gone up basically close to 400 megawatts. And the actual energy produced is on the right. And you can see once they were installed, they produced pretty uniform energy, except there was a dip in 1991. Anybody want to hazard a guess why this plant had a lost power in 1991? Not an earthquake. What is in the back? Close. Mount Pinatubo in the Philippines. Yeah, when those sulfate aerosols from Mount Pinatubo get released, you get solar dimming, and we could actually see that in the plant. This is the resource. Now, concentrating solar power, if you're tracking the sun and concentrating it, you can't use diffuse radiation. It has to be really bright, clear skies. And so that's why this resource is really, by far, best in the Southwest. So that's the resource. Now, you look at that resource and you say, well, let's look at what's practical. And so we apply various filters and we say, we're going to exclude these things. Used in sensitive land, any solar less than 6.75 kilowatt hours per square meter per day. What does that mean? It means we're only using the very best resource. And if the ground slope is greater than 1%, well, we don't want to deal with leveling the land. We're going to exclude that. After we exclude all those things, this is the map you wind up with. This is what's left over. So if you look just in the states there, those little blobs of color show you where are the best places where it really makes sense, where we can really install this solar. All right, so if we install concentrating solar power in these locations, what will we have? We'd have 7 times the U.S. electric generating capacity. That's how much we could get from those sites. Now, I don't usually like to include tables of numbers in presentations, but I thought since I'm here in Utah, I should at least show you Utah numbers, because you might be curious how Utah fits into this. And you can see, if you look down that center column, Utah could provide 456,000 megawatts of electricity from concentrating solar power. Now, I don't know what I couldn't get on the internet this morning, and I was going to try to look up the peak power capacity in Utah. In Colorado, in the summer, it peaks out at about 11,000. So I got to guess Utah is somewhat less than that. So I don't know whether you're 7,000 or 8,000 or whatever. But the point is, you could get 456,000 megawatts from concentrating solar power. So let's just say more than enough power than what you need. Now, studies have been done in Europe and transmitting this power, for example, putting parabolic troughs in North Africa and then transmitting it with high voltage DC transmission lines across the Mediterranean to Europe. We could do something similar in the US. It'd add to the cost, probably a couple cents a kilowatt hour, but we could, if we can get over rights of way and that sort of thing, move electric power from the Southwest to the eastern part of the US. The nice thing about that, if we move power east, when those eastern utilities are still peaking in the summertime, we still have sunlight in the west, which is kind of a nice arrangement for us. Okay, so I tell you this study looked at all these different technologies. Concentrating solar power looked at parabolic troughs with 6 hours of thermal storage and came up with 80,000 megawatts of power, 6 to 13 cents a kilowatt hour. And remember that 1,200 million tons of carbon per year we're looking to displace by 2030? Out of that 1,200, concentrating solar power would displace 63. And, you know, now looking at it from what I'm seeing with the industry, I think even going higher than that is quite feasible. I do want to point out, though, that there have been a lot of new plans. For example, there was just an announcement of a new 280 megawatt plant being installed by, being built by Arizona Public Service. But one of the issues is this investment tax credit. It is still too expensive. We need the investment tax credit. Right now it expires at the end of 2008 and we need it extended. And these two plots show you what the marketing people think is going to happen. The blue line is without the tax extension and the red line is with the tax extension. So what Washington does has a big impact on what we can see happen out in the field. Okay, photovoltaics. Now photovoltaics, certainly you can do central power with photovoltaics. You can use concentrating PV, you can use flat plate PV. But most of the work on PV in recent years has focused on putting it on rooftops because PV is still relatively expensive. And if you put it on your rooftop, instead of competing against the wholesale price of electricity, you're competing against the higher retail price. So you get away from all those transmission issues. And that's one thing PV can do, is you can put it right on the rooftop. So the study for the American Solar Energy Society looked at that. Now here's the PV resource. Again, it's still best in the Southwest, but it doesn't need direct sunlight if it's not tracking. It can collect diffuse sunlight, so it could be used across the country. And in fact, the country that has installed more PV in recent years than anyone else is Germany, and their resource is less than what we have in Illinois, Chicago, for example. Now, of course, they have some financial incentives and high prices of electricity that push that market. Okay, so we're looking at grid-connected PV. One of the things that people that have PV like is they love to watch their meter running backwards when they're selling electricity back to the, they always bring people over and show them their meter going backwards. Probably about between $5 and $10 per peak watt, about 20 to 30 cents a kilowatt hour. So again, pretty expensive. It needs some support, some tax incentives. But if you include it into the mortgage of a new house, certainly you could see immediate savings in your monthly bills. I just want to show a couple things, a couple slides indicating what's happening with PV. This shows you PV module prices. The green curve is what it was in that year. Probably more relevant is normalized to 1 year that takes into account inflation and everything. And you can see from that blue curve, very, very dramatic drop in the price of PV over the years. These are worldwide PV shipments. This is a technology that's just going exponentially. And every year we add a new bar to this graph thinking maybe it's going to start to level off. And I haven't seen it happen yet. So. This is a busy graph, but I just want to make 2 points with this. This shows you what's happening in terms of improving cell efficiency. So 2 points to realize. Those different colors represent different PV technologies. So the nice thing about PV, they're all different. Besides the commonly used crystalline silicon, which is probably 90% of what you see installed, there are various thin film technologies, other types of PV technologies. A lot of materials research going into this. So each of those colors represents a different technology. And the one common thread you can see from all those colors, that versus time, the efficiency is going up. With these triple junction cells that are used in space and can be used with concentrators on the Earth, you can see they've now top 40% efficiency. They're very expensive, so that's why we look at concentrating sunlight so we can minimize the amount of cell area. Okay, so in this study for the American Solar Energy Society, came out with 200,000 megawatts peak installed on houses by 2030, costs ranging from about 28 cents per kilowatt hour today, and then as we approach 2030, expect costs to drop to around 6 cents per kilowatt hour retail. 63 million tons of carbon per year out of that 1,200. Okay, so the last technology I'm going to cover this morning is biomass and biofuels. There are various ways to produce this. Here's a map of the U.S. showing that we have a lot of resource in the western part of the U.S., a lot of resource in the Midwest. So in biomass, we're talking about two things. One is to produce electricity. The other is to produce fuels for transportation. So how do you produce electricity with it? Well, you can burn it directly. You can co-fire it, meaning you mix it with coal in a coal burning plant. And that's being done to a certain extent. And you can also gasify it and basically turn it into hydrogen, burn the hydrogen. What about biofuels? Well, there's two basic routes. The one we're working on probably most at NREL the National Renewable Energy Lab, is the top one, sometimes called enzymatic hydrolysis, where we basically take cellulosic ethanol, that's sort of like corn stalks, that sort of thing, not the corn itself, and turn it into ethanol via fermentation. And the other high temperature processes, pyrolysis, gasification. And this shows you the lab equipment that we have at NREL. On the left is the typical fermentation process for producing ethanol, but what's different is instead of using corn, we're looking to use cellulosic ethanol. And the right shows cellulosic ethanol heated to very high temperatures to produce fuels. So if you look in the US right now at biopower, there's about 10,000 megawatts of power produced by direct combustion, 400 megawatts from co-firing with coal. Biofuels, there's some biodiesel, but most is corn ethanol, and that's a 2005 number, and I guess I better update that because the corn ethanol industry has really taken off in the last couple of years. Cellulosic ethanol is what we're really interested in because it's a lot more energy efficient, but the cost is high, so we need to get the cost down. It's not easy to take this plant material like corn stalks. It's pretty rugged stuff, and breaking it down and fermenting it is not easy. I wanted to show this graph from the Union of Concerned Scientists to illustrate that this shows you carbon emission savings relative to gasoline. And what you can see is these three are corn ethanol. So depending on how you do the fermentation process of corn ethanol, depending on what you use as a heat supply, you can actually produce more carbon emissions than you would from gasoline, or less carbon emissions. And this is probably typical. About maybe corn ethanol on average reduces carbon emissions about 20%. If you go over to cellulosic ethanol, that's 80, 90% reduction in carbon emissions. Now, there have been some articles recently that look at land use effects, so we have to be careful. If we compete with food, for example, and we raise food prices and we cause people in Indonesia and South America to burn rainforest and start growing crops, we can actually contribute to global warming, make the problem worse. So we have to be very careful when we look at the whole system. Also, you've heard of people turning coal into liquid fuels. Unfortunately, that's probably the worst thing we can do from the standpoint of climate change. So biofuel savings, we looked at producing cellulosic ethanol from crop residues in energy crops, and the cost would range from 90 cents to $3.75 a gallon gas equivalent, a savings of a little under 60 million tons of carbon per year. Biomass power savings at 5 to 8 cents a kilowatt hour would save about 75 million tons of carbon per year. So how does this all add up? Well, here's a map of the US, and I'm not just going to show you the technologies I covered this morning. I'm going to show you all of them on this map. But on the lower left there, you can see these bars indicate, that bar indicates how much carbon emissions we'd have to reduce by 2030 in order to be on the path for an 80% reduction by mid-century. This is what we need to be on the path for a 60% reduction by mid-century. So we're going to add these different things, and then there's a bar showing how much each can contribute. Well, I didn't cover energy efficiency today, but that's the big thing. So when you hear people talk about how important energy efficiency is, they're right. Because energy efficiency from our study indicated we could displace almost 700 million tons of carbon per year, about 57% of the total. That's wind power. That was the biggest renewable contributor as we saw it between now and 2030. And I believe you had a presentation on wind energy yesterday. And that's where it would be distributed. And you can see Utah has a good resource. That's photovoltaics. That's concentrating solar power. Biomass and biofuels together. And finally, geothermal. And the point is, all these renewables together can be in the ballpark of where we need to be in terms of total carbon emissions. And we didn't force it to be this way. We didn't say, okay, we got to achieve this target. We just asked the experts, how much do you think you could really do in a strong climate-driven scenario? And this is how it came out. Now, this was not a fully integrated study. We integrated as much as we could from our models. So there could be some overlap. But we were careful, for example, not to double count biomass used for biofuels and for electricity. This is how it looks on a wedges map. The big wedge there on the top is energy efficiency, and those colored wedges are renewables. Now, one of the things I did is I looked at the cost. What would be the annual cost between now and 2030 of doing this? So geothermal would cost us $2 billion a year. $7 billion a year for concentrating solar power, 5 for PV, 3 for, and PV is cheaper because we had it coming on much later. Okay, but if I add all these different renewables, you get about $26 billion a year. Now, I think we're spending over $100 billion a year on the Iraq War. And regardless of what you think about the Iraq War, the point is that kind of money is being spent for something the administration believes is important, and it hasn't bankrupted the economy. So we could spend $26 billion a year to address climate change with renewables. But the really good news is that the efficiency would save us $108 billion a year. So if you package this all together, it's a net savings of $80 billion a year, if you really bundle all this together.
Wind is free there?
Yeah, between now and 2030, based on how we expect to happen, these are net relative to the regular electricity prices. Yes, wind winds up being just about break even between now and 2030. Okay, so that's for the U.S. I just wanted to say a word about inaction. There was a report recently by the University of Maryland on the U.S. economic impacts of climate change. What if we don't address it? What if we have to clean up all the damage? What's it going to cost us? Their conclusion was delayed action or inaction will most likely be the most expensive policy option. So what's the most expensive thing we can do regarding climate change? Nothing. That's the most expensive thing we can do is ignore it, because we're going to have to pay for the damages. And Nicholas Stern of the World Bank did a review that estimated the cost of inaction would be 5 to 20% of the world gross domestic product, whereas addressing it would cost less than 1%. We did a similar study for Colorado. I think you could do something similar for Utah. And you can see those top 3 color curves are energy efficiency, electric efficiency, natural gas savings, and transportation efficiency, and then renewables below that. Same sort of thing. What efficiency does is more or less level out emissions, and the renewables allow us to make those deep cuts that are needed. And in this study for Colorado, we had a net savings of $4.6 billion. That's not per year. That would be between now and 2030. The other thing is the Union of Concerned Scientists looked at the impact of a national renewable electricity standard. Government comes out with a law that says must produce 20% of our electricity from renewables. What would the impact on Colorado be? 185,000 new jobs, 3 times what fossil would produce. $25 billion in income to farmers and ranchers. Farmers and ranchers love the idea of getting paid $3,000 to $5,000 for every wind turbine they get on their property. Some of them make more money from their wind turbines than they make from their crops or from their ranching. $30 billion in consumer savings by 2030. One of the things you do is when you use these other fuels, the cost of gas, the cost of oil come down. It's supply and demand. So this is where you can get more information. I know that was a real quick tour of some of these technologies. And I guess the point of these photos is you've probably heard people say there's no single silver bullet. There are many different solutions, but if we apply all those different solutions, and there are different solutions in different parts of the U.S., we can address this problem. And for more information on the research that's going on in renewable energy, I encourage you to go to the National Renewable Energy Laboratory website, www.nrel.gov. Thanks very much.
So again, just like yesterday, please do raise your hand. We'll get around to you. And I think in the interest of time, we have about 2 questions we can try to take.
You said by 2012, 2013, the sea ice would be gone.
Some scientists believe that summer sea ice,
All right.
September, will be gone as early as 2012.
The Maya calendar ends the world in 2012. December 21st. That's a very spooky day.
Now you really got me scared.
So, question from yesterday again. Since efficiency is such a big part of your solution right here in front,
Okay.
the rebound effect, you increase efficiency, you just enlarge the economy, use more. You don't get any net effect from efficiency.
I don't really buy that argument. I don't really buy that anti-efficiency argument. You know, it's sort of like the idea is, well, you know, if you double the gas mileage of a car, people are going to drive twice as far. Well, I just don't think that if you get a car with twice the gas mileage, you're going to decide you have to work twice as far away from your place of employment. That's not going to happen. I don't think vehicle miles traveled is going to change that much just because fuel efficiency goes up. And I think similarly, I think if you replace all the incandescent lights in your house with compact fluorescents, I mean, I don't think you're going to use, you know, turn on the lights 4 times as often as you did before. I just don't see that happening. So.
But you might buy something else, a flat screen TV from China and they build.
Yeah, conceivably, but I think, you know, when we look at energy efficiency, you just look at what's happened to refrigerators over the last 20 years. The refrigerator you buy today uses a tiny fraction of what a refrigerator used 20 years ago. Now, it's true that people are buying DVD players and things like that have what are called vampire loads. And those are things that they sit there in the standby mode and using electricity even when they're not on, okay? But I don't think that's because people are putting in compact fluorescents. I think it's just that our technology is changing, our entertainment's changing, these things are becoming available. What we have to do is we have to address those vampire loads. We have to pass national, federal standards that don't allow your PC and other things to be burning a lot of electricity while they're in standby mode, and I think that can be easily alleviated, but we need some legislation to do it. Yeah?
I was curious if you could talk about the lag time between the rise in CO2 and the rise in temperature.
Okay, well, you know, we could probably spend hours and hours answering the skeptic arguments, okay? Let me just answer that one. I don't know if we have time, but I'll try to give a succinct answer. If you look at the ice core record that goes back 650,000 years, we went in and out of ice ages at about 100,000 year cycles. And if you look at how the temperature varied, and we won't get into the details about how they figure that out, but they extract air bubbles from the ice and they can infer the temperature, and they can actually directly measure the CO2 content. And what we see, and if you remember from Al Gore's graph, it shows temperature going up and down and carbon dioxide going up and down. So what the skeptics have said is, wait a minute, the temperature occurs before the carbon dioxide. Well, as often happens in arguments like that, there's a kernel of truth to that. In fact, what happens is orbital parameters change. Okay, and in this particular case, the eccentricity of the Earth's orbit changes the solar distribution at the north and south poles relative to the center. That causes enough heating at the poles to cause melting of the ice and get us out of an ice age. Okay, it's enough to start it. It's not enough to cause the 5 degrees Celsius temperature swings. If you do any modeling of it, those slight variations in temperature, those slight variations in solar radiation distribution can't really explain going in and out of ice ages. What can explain it is the CO2 feedback. As the temperature rises, carbon dioxide gets emitted from the oceans, gets emitted from the ice, the permafrost. That greenhouse gas, all right, causes a positive feedback which allows that temperature to keep going up. So there was a Serbian scientist named Milankovic who first proposed it was these changes in Earth orbital parameters that cause us to go in and out of ice ages. The reason nobody believed him is because they calculated the change in solar and it was just too small to explain it. As soon as you bring in the positive feedback from the greenhouse gases, then you can explain it. So it's really irrelevant that the temperature occurs first. I will also say there are many cases in the paleoclimatic record, earlier than the ice core data, where we have data that shows sudden releases of greenhouse gases into the atmosphere. And when that happens, the temperature follows. You don't see it in the last 650,000 years, but millions of years ago, there are a number of instances where sudden release of greenhouse gases caused the temperature to follow. It's really basic science. And if you look at the IPCC models, they run their models with and without man-made effects. And only when they put in the greenhouse gases in the models do the models predict accurately what's happening to the temperature. Okay, and I think we're out of time. Thanks very much.